Hello, my name is Noah Abji, and today we are going to learn how to find the prime factorization of any number. So let's begin. So you'll notice that prime factorization is made up of two main words, the word prime and the word factorization, which sounds like factor. So if we don't know what those are, the best place to start with prime factorization, before explaining what it is making sure that we know what a factor and a prime number is. So here's what a factor and prime number is. A factor is basically a number that goes into another number. So if I had a number x and a number y, if y was divisible by x, then x is considered a factor of y. Now, if that didn't make sense, let me give you an explanation with some actual numbers. So let's say I had the number 30. Now, the number 6 goes into 30 because 30 divided by 6 is a nice 5. It's a whole number. It's not a decimal or anything. So that's why we would say that 6 is a factor of 5. 30 is divisible by 6. Let's look at another example. If I had the number 4 and the number 2, 2 is a factor of 4 because 2 goes into 4. Because 4 divided by 2 gives us a whole number. The answer is 2, and there's no decimals or anything. Therefore, 2 is a factor of 4. 4 is divisible by 2. So those are what factors are. Now, some numbers aren't factors. So for example, if we had the number 16 and 5, 5 is not a factor of 16 because 16 is not evenly divisible by 5. If I did 16 divided by 5, I end up with 3.2, which has a decimal at the end. We don't get a whole number. And since it's not divisible, then 5 is not a factor of 16. And so just like this, you can list all the factors of certain numbers. So for example, the factors of 12 are 1, because it's divisible by 1, 2, because it's divisible by 2. 12 divided by 2 is 6. 3, because 12 divided by 3 is 4. 4, because 12 divided by 4 is 3. Not 5, because that would give us a decimal when divided. Then 6, 12 divided by 6 is 2, and 12. 12 divided by 12 is 1. And so 12 has 6 total factors. And every number will always have 1 and itself as factors. So that's how factors work. Now, prime numbers are something special. They have something to do with factors. And that's that they only have 2 factors total, which are 1 in itself. I told you that every number will always have 1 in itself as a factor. If I had the number 385,000, even if I didn't know what any of the factors of this were, I could automatically say that 1 and 385,000 are factors of 385,000. But there are some numbers that only have those as factors. So let's look at one example. The simplest prime number that I can think of is 2. 2 is a prime number because the only numbers that 2 is divisible by are 1 and 2. It has 2 factors total, 1 in itself, so therefore it is a prime number. Another prime number is 3 because the only factors of 3 are 1 and 3. So therefore it's also a prime number. It has 2 factors total. 4 isn't a prime number because it's divisible by 1, 2, and 4. So it has 3 factors, and prime numbers only have 2 factors, 1 in itself. So here are some examples of prime numbers. And you should try to memorize these at some point because they'll be useful for other things that you may do with them. So they're 2, 3, 5, 7, 11, 13, 17, 19, and 23. And these are the first 9 prime numbers. And I'll throw one more in. The next prime number is 29. So those are the first 10. And 2 is actually the only even prime number because all other even numbers are divisible by 2, meaning they can't be prime. Now, one last thing before we move on. One common misconception about prime numbers is that 1 is a prime number. That's not true. Even though the only factor of 1 is itself, so it's 1 and itself, part of this definition includes the and. and signifies that it has two factors total. The only factors can be one in itself, and there has to be two of them. But since one only has one factor, it's not considered a prime number. So the next thing we're going to learn is about the fundamental theorem of arithmetic, which sounds scary, but is actually something that's really simple. And that says that any natural number, so basically a whole number greater than 1, can be written as the product of only prime numbers. So basically, it can be broken down into only prime numbers multiplied by each other. So let's look at some examples. So for example, the number 4 can be written as 2 times 2. 2 times 2 is 4, and 2 and 2 are prime numbers. 33 can be written as 3 times 11, because that equals 33, and they're both prime numbers. Now, 44 has many more factors than just 2, 2, and 11. It's divisible by 4, it's divisible by 1, it's divisible by 44, and it's divisible by 22. However, we can break it down into just 2 times 2 times 11. So only using prime numbers to write out what 44 is. 2 times 2 is 4, and then times 11 is 44. And 54, an even bigger number, can also be written as just the product of prime numbers, just 2 and 3 in fact, because 2 times 3 is 6, times 3 is 18, and then times 3 equals 54. And this is true for every single number. Now, all these prime numbers are factors of these larger numbers. And the reason that this works is because if you think about it, let's look at the example of 44. Let's say we were to break 44 down into 4 times 11. Now, 11 can't be broken down any further. But since all numbers that aren't prime have more than two factors, we can break down 4 even further. In fact, 4 can be broken down to 2 times 2. And since these are prime numbers, these can't be broken down any further. So we actually end up with 2 times 2 times 11. And this is what we call the prime factorization of a number. Well, we actually break it down into only the prime numbers multiplied by each other. So 2 times 2 is equal to 4. So 2 times 2 is the prime factorization of 4. 3 times 11 is the prime factorization of 33. 2 times 2 times 11 is that of 44, and 2 times 3 times 3 times 3 is the prime factorization of 54. And this is where the words come from, factorization, breaking it down into factors, and then the prime part means that they're only prime factors. So just like I explained, prime factorization is when we take a composite number and write it as just a product of only prime numbers, and that's using the fundamental theorem of arithmetic. Now, I gave you some examples on the last slide. Now we're going to learn how to actually find the prime factorization. And it actually involves a little bit of drawing. So this is what I call the tree method. And we're going to do it together with an example. So we're going to make a tree diagram. And the way that we do that is we take the number that we want to find the prime factorization of, and we write it kind of near the top of the page, because we're actually going to be writing stuff in this area below. So our first step is basically, and like I showed before, you can break numbers down into a bunch of different numbers, and it'll eventually lead to prime ones. Break it down into two numbers that multiply to get 680. So let's do this using a tree. So we're going to draw little branches from 680. Here's how this looks like. So we know that 68 multiplied by 10 is equal to 680. And we don't have to worry about breaking it down into prime factors for now, because no matter what you break it down into, this is always going to work. So break it down into two numbers that multiply to get your original number. And this is how we start the tree. So we get 68 and 10. So now let's do that for another layer. Both 68 and 10 are not prime numbers. They're composite numbers. So they can be broken down even further. So we're going to repeat this until only prime numbers at the bottom of this tree are going to remain. So with 68, it can be broken down into 2 and 34. And then we can break down 10 into 5 and 2. Now what you'll notice after we broke these down is that some of these numbers are prime. So when we broke down 68 into 2 and 34, we got 2. And 2 is a prime number. So there won't be any branches coming off this 2 because we can't break it down any further. However, 34 can be broken down even more. Because 34 isn't a prime number, it's divisible by 2. It's an even number, so it has to be divisible by 2. And when we divide it by 2, we can break that down into 2 and 17. And so now you'll notice that at the bottom of this tree, we only have prime numbers. This 2, and this 2 are all prime, so we can't break it down any further. This 17 is prime, so we can't break that down any further. And 5 is also prime, so we can't break that down any further. And so this is how we find the prime factorization. All you have to do now is count. At the bottom of our tree, count how many of each prime number we have. Well, we have 3 2s, 1, 2, 3. So we can start by writing 680 is 2 times 2 times 2. Then we have a 5, and only numbers at the bottom of your tree count. So we're not going to include the 10, the 68, or the 34. So we multiply by 5, and we have a 17 at the bottom, and that's also a prime number. So we write the 17. And just like that, we've broken down 680 into its prime factorization. 2 times 2 times 17 times 5 times 2. And sometimes it's a little bit better to write it in numerical order, so it actually should be all the 2's at the beginning, then the 5, and then the 17. But if you're writing it just as you counted from the tree, you get a 2, another 2, a 17, a 5, and a 2. And this is going to work for every non-prime number. You can use a tree diagram and break it down into numbers that multiply by each other to get that original number. So 68 times 10 is 680, 2 times 34 is 68, 5 times 2 is 10, and so on. And you will always be left with only prime numbers at the bottom of your tree. When you count those prime numbers up and multiply them by each other, that's your prime factorization. All right, and finally, let's do a review question. Here's the question. Find the prime factorization of 120. And you should use a tree diagram to do this. If you'd like to give it a try, I'll give you a few seconds to pause the video before explaining the answer. All right, so the correct answer to this question was 2 times 2 times 2 times 3 times 5. So just like any prime factorization, we're going to make a tree diagram and start by writing 120 at the top. You're going to need some space below, so if you're using a piece of paper, make sure to write it at the top of your paper. And if you're using something online like this, just leave some space below this 120. Now we can break it down into any two numbers that multiply to equal 120. And just to prove that this works, I'm actually going to do two different tree diagrams and start by breaking it down into two different numbers to show you that it doesn't matter what you break it down into, you'll always end up with the same prime factorization. So for this one, the easiest thing I see is that we can break it down into 60 multiplied by 2, because 60 times 2 is 120. Now, this 2 is a prime number, so we can't break it down any further. So the only part we can break down is this 60. Now, since it ends in a 0, it's an even number. That means it's divisible by 2 again. So let's divide it by 2. We end up with 2 and 30, because 30 times 2 is 60. Now again, this 2 can't be broken down, but this 30 can, because it's an even number. So let's divide it by 2 again. So dividing by 2, we get a 2 here and a 15 here. 15 times 2 equals 30. Now this 2 can't be broken down, but the 15 can. Now we can't divide it by 2 again. However, we can divide it by 5, and we know that because it ends in a 5. So if we break 15 down, it's 5 times 3. So we can write a 3 and a 5 at the bottom here. And now we have all prime numbers at the bottom of our tree. These 3 2's, the 3, and the 5. So if we count the numbers only at the bottom of our tree, we get 3 2's, so 2 times 2 times 2. A 3 right here, so times 3. And then a 5, so times 5. And that's our prime factorization of 120. Now, just to prove that this works, even if you didn't break it down into 60 and 2 at the beginning, I'll do another tree diagram and actually break it down into different numbers that aren't 60 and 2. So let's break it down into 8 and 15. 8 and 15. 8 times 15 is 120. And we could have chosen a whole number of different factor pairs, such as 6 and 20 or 5 and 24 that multiply to get 120. But I'll go with 8 and 15 because this will make for a nice tree. So both these numbers are not prime, which means that we can break them down further. 8 is divisible by 2, obviously, so we can break it down into 2, and then 2 times 4 is 8, so also 4. And 15, like we saw before, is divisible by 5. So let's break it down into two numbers that multiply to get 15, one of which is 5, so the other must be 3. So we have 2, 4, 5, and 3 at the bottom here. Now, the 2, 5, and 3, these are all prime numbers, so we can't actually break them down further. But this 4 here, this 4 is not a prime number. So we can actually break it down a little bit more. And 4 can be broken down always into 2 times 2. And these are prime numbers. 2 is always a prime number, so we can't break it down. And we're left with only prime numbers at the bottom of our tree. And just like before, we have 3 2s right here, a 3, and a 5. So we end up with 2 times 2 times 2 times 3 times 5. And we get the same answer, and we have different tree diagrams. So this is why the tree diagram is really nice. You only have to think of two numbers, any two numbers, that multiply to get your original one. And then you can break it down from there and so on in easy steps, and you'll find the prime factorization. That's all, and thank you for watching.